Right, welcome everybody to Automated Flight Lecture 1, where we will have an introduction to the first lesson and some basic control theory. So today's program is, we've had the course objectives and the program already in the introduction. We will start with control theory terminology, some system configurations, different fields of application, and we will have some complex analysis, the mathematics behind the control theory, which will be in a separate lecture, a separate video. We base our first lecture, the math of the first lecture, on this book. This is the 5th edition. The 4th edition works fine too, and basically it is most of chapter 11, where we will ask you to do the end of block exercises for block 1 through 4 and 5, part of 4 and part of 5, the blocks really that are appropriate for this course. Now in 1903 the Wright brothers had the first powered flight, and of course, because it was there was nothing else besides the control inputs, this was a hand-flown flight. And as aviation developed, there was a more need for automation. And the automation came rather quickly in 1914, when Lawrence Sperry used gyroscopes to stabilize a plane. And here you can see Lawrence Sperry in the pilot seat with his hands in the air and a mechanic on the wing, and this demonstrated that autopilot was possible, and that even disturbances in the weight of the plane could be compensated for by the autopilot. In 1937, Crane and Holloman illustrated that it was also possible to automatically land the plane without input from the pilots, and even before the Second World War, all these automation systems were already possible. Now, nowadays, we see a lot of automation in the cockpit, and one of the most common things, of course, is the autopilot, although there are many systems that have a different control system attached to it, like the cabin pressurization and the heat. But the autopilot is one of the control systems that speaks most to the imagination. Here we have taken out this panel, and the flight control unit, or the automatic flight control system, can do many things. And one of them is maintain altitude, attitude, heading, and speed. It can also follow navigation aids like the VOR or GPS waypoint, and it can assist in the approach and landing. So these are this is a system within the plane that controls the behavior of the plane. Now, every system has a certain process, the speed, the altitude, the heading, the approach and landing, but it also needs actuators to make sure it does that. And the autopilot makes good use of the flight control surfaces, the ailerons, rudder, elevator. There are many different ones, and of course the engine controls. The autopilot can automatically engage the throttle. So we see that a system has a process, namely the altitude and speed, and it has actuators, such as the flight controls and the engines. Now, we always start with a system, and the system, as I described before, is a combination of an actuator and a process. Now, systems can be very simple and, of course, very complicated, like an aircraft, but even your household toaster can be seen as a system. It has a heating element that is our actuator, and our process is browning bread. The central heating system, just plainly the central heating system, is a burner, and the process is heating up a space in a house, for example. We have a car. We want to provide power to the wheels. We want to accelerate. We want to get somewhere, and we have as an actuator the throttle, which controls the fuel and oxygen flow to the engine. And of course, an aircraft with control surfaces and its engines will control speed, roll, pitch, yaw, and many other properties. Now, before we go into modeling even a simple toaster, let alone an aircraft, we need a physical model. We need a simplification of reality to ensure that we can still manage the system. Here, of course, we make assumptions. A lot of behavior is reduced to, for example, linear systems, like the second-order differential equations we saw in engineering, mathematics, and modeling, and we'll use classical mechanics to derive the model. Well, here in this video, this slide, you will see a mass spring damper system. Over here, where we have a damper, a spring, and a mass, and an external force, and this will yield a second-order linear differential equation that we may want to change the behavior of. So for this example, we see, let me see if I can, we have an external force which drives the behavior of the system, but our mechanical properties, such as the mass of the system, the damping of the system, and the spring constant, they will dictate if any force applied to it will result in oscillations or just a simple damping back to a steady state situation. Now, if we look at our mass spring damper system, we have modeled that as a second order differential equations with force as an input. All right. So we have our force as our input, and if we look at the block diagram of a system with its inputs and outputs here, the force applied to the mass spring damper is our input. And what do we measure? Well, we measure the displacement of our system, x, and that is the output of the system. So a system can be something as simple as a mass spring damper system, where we have modeled in a simpler way using a second order differential equation, and we can see that we have built our first system, and it has two properties that we put in a functional block diagram to describe the system with an input and an output. Now, this example has a single input and a single output, and these are the systems that we will be talking about mostly in this course. But of course, there are different configurations. Here we have a single input, single output. You can also have multiple inputs and multiple outputs, or just a single input and multiple outputs, or multiple inputs and a single output. All of these have abbreviations that are rather self-explanatory. Now, in control theory, we can distinguish two types of systems. The first one is an open loop system, and the second one is a closed loop system. Now, a good example of an open loop system is a toaster. There is usually one knob on a toaster, which for some strange reason goes from 1 to 5, or has a sliding scale. You set it, you turn the toaster on, and you wait. If you set it correctly, you get the toast you want. If you set it incorrectly, you will get burnt toast or simply just bread. There is no control system in place, no control loop that will make sure that you get exactly the type of toast you want. Now, with central heating, there's a different system. We have our heating system, we have our radiators, but we usually also have a thermostat. The thermostat reads the temperature in the room, which is the output we're trying to control, and tells the burner to turn on or turn off if the temperature gets too low or too high. And this way the temperature in the room stays pretty much constant, although there will be some variations. So the toaster is an open loop control system where we have an input and an output, but we have no way of managing the behavior. A closed loop system takes the output, in our central heating example, the temperature of the room, feeds it back to the system to make sure that the system has the desired behavior, namely a comfortable temperature in the room. So the open loop system has no feedback, just simply the properties of the system, and a closed loop system takes the output, makes a comparison with the desired input, and uses that error to control the system. Now, in a functional diagram, we have a couple of elements that are important. We have our input and our output, of course, and the system. If we split a signal like is done at the output, we call it a branch point, and when two signals come together, it will be a summing point. Now these signals can be added to each other, but can also be subtracted to each other, and typically if they are subtracted at the point on the left of this diagram, you get an error signal, which is not shown here. But positive feedback is also possible. It is also sometimes a property of physical systems themselves, and that a positive regenerative feedback signal is just inherent in the system. And I'll show you some examples of that later. Now, typically, to control a system properly, we can't just use the output and add it or subtract it from the input. There is typically a controller that ensures that the behavior of this feedback signal is used in such a way that the output is desired. You can imagine that if we are driving a car and we wanted to stay in a certain lane, that deviations must be controlled so that the car is in the center of the lane again. Well, you do not want this to happen too slowly, because then any deviation will be controlled, will be rectified too slowly, and you might deviate onto the other side of the road. And you also don't want to be the passenger in the back, where the driver immediately corrects errors, leading to a very jagged, uncomfortable output. Well, feedback signals are usually generated by sensors, like temperature sensors in a central heating system, or the lane control system in the car will use cameras to determine the distance from the lines marking the road. So in aerospace we have many different types of control systems, and I would like to show you a short bit of a video from one where we look at an autopilot where students of another university created a model of an aircraft and implemented a control system to fly a plane. This is hand flying. The red line is a trajectory, and you can see if you have to hand fly a trajectory with, I guess, a toy model, it can be rather difficult. But you can imagine that flying through very difficult weather, through clouds with zero visibility, it might also be very difficult to control an aircraft if you rely solely on hand flying. So this is an example, and I'll scroll through this video a bit quicker, and of course the link is in the description, where they design a controller, a PID controller, a type of controller that I'll get this back, that we will also be using, where we have a desired trajectory. We have an actual trajectory here. We have the aircraft as a system, we have our controller, but we also have disturbances. And of course, in every physical situation, which is not ideal, you will have disturbances to the system. Well, you saw the hand flying a while ago. If you compare this to to what they're able to do with the controller, And here they're describing the different types of control: heading control, altitude control, and control to turn a corner. And you will see that instead of a very disturbed flight trajectory, this controller is able to steer fairly well along the desired trajectory. And you will see it will not follow the line perfectly, because controllers have certain limitations, and you also want to keep in mind that you don't want to control too fast, like in the car example, and here as well. So there will be a bit of a delay in response, or a response which is too little, and there'll be some overshoot where it tries to find its trajectory, but will overshoot in altitude and in heading a bit. But these are properties of control systems that we will just have to accept. All right, so back to our presentation. So one of the things that can happen is that we have a system that is not inherently stable, and we want to stabilize it ourselves. Typically you have a negative feedback loop for that, but positive feedback signals also happen, but also happen in physical systems themselves, or where a pilot, a human operator, might be flying a plane. So if we look at another video here, and let's go to this one. This is a video of a plane landing with the pilot at the control. It looks all fine, and then there is a disturbance, and the pilot reacts to this, causing oscillations of the plane. The plane goes up. The pilot makes a very large movement to compensate. The plane pitches down, and you see that the oscillations, compared to the small oscillations at the start, become larger and larger and larger until the pilot eventually regains control. So here the oscillations are small, but due to pilot input, they become larger and larger and larger. And you see that also with cars. If they have to make a corrective movement, the oscillations become small at first, but because the system takes that feedback and it adds to the system, you get this wild behavior that causes the car to ultimately spin. So positive feedback is also possible in certain situations. Now, from here I have a couple of videos explaining the concept of ground resonance in helicopters. So you can see that as a force that we have from the rotor blades that can be lift. But what can happen is if there's an imbalance in the rotor blades, there will also be a lateral vibration. Now the helicopter and the landing gear act as a mass spring damper system, and if the mass spring damper system is configured in such a way, the input of the rotor head can actually cause oscillations in the helicopter, and these oscillations can get worse and worse and worse, and if they aren't stopped, the helicopter will be destroyed. So I will show you some videos of that. Let's see. First, well, let's see a couple where it does actually break down. So this is a Schweizer 300 helicopter. It's lifted up, it gets set down, vibrations occur, and nothing is done, and the helicopter self-destructs itself rather violently. Luckily, these pilots walk away. Another one with a bigger helicopter where you see initially small vibrations, but because the vibrations aren't dampened in any way, the helicopter isn't able to lift off the ground. The landing gear and the rest of the helicopter just shake itself apart. Now that doesn't always have to be the case. Here is a video where if nothing had been done, the result would have been the same. Here the helicopter is set down, and it's set down rather harshly. This is a video of a student pilot who, well, in a couple of first lessons, set the helicopter down rather abruptly. This caused the three-bladed helicopter to have blades that are not 120 degrees apart, but some are closer together and some are further apart, which starts a wobble in the helicopter. I know this text is in Dutch, but it doesn't really matter because this is just simply an explanation of what's happening. This face of the student looking rather puzzled about what is happening is my face. Luckily, I had my instructor next to me, and the wobble gets bigger, and the solution, if there is no problem with the helicopter, is just to lift off. Then the resonance in the landing gear stops because there is no ground to push against. So luckily that can happen as well. Well, these of course are very strange situations, but there's another class of things that wobble, and this is not the one I want. This is the one I want, where we here look at a PA-28. This is a NASA video where we're looking at a plane under high wind conditions, and you see the one of the control surfaces start to wobble, and this wobble will become worse and worse and worse and worse and worse if the conditions are not changed. Now you can imagine that this might lead to structural failure, and that it causes disaster. And of course this disaster is the introduction to another bit of video where we see the Tacoma Bridge, where the bridge has properties that in the right wind conditions the bridge gets wobbled a bit, and in such a way that it starts resonating. And I guess everybody knows this example, that the bridge wobbles and the oscillations become worse and worse and worse, and eventually the bridge collapsed. So we can have this on physical systems where there is no pilot or controller input. There are just physical properties with some kind of input like wind that can cause physical systems to start resonating and break. So we'll stop this. Well, the crash obviously eventually the whole middle structure collapsed. Now we do not want that in any physical system, also not a bridge or a helicopter, but we also don't want excessive unstable behavior in an aircraft. Now, so I think that was this is our last slide. So what we want to try to show in this course is that we can model behaviors, and we will mostly do that in mass spring damper systems, and we can analyze the behavior of a system so that we can add a controller to ensure that we don't get excessive oscillations, or that we don't get an output with a controller that is too jagged or too slow, or just very, very, very slowly oscillating to a desired set point. We will look at different types of controllers, and we will implement a proportional controller later in lectures in weeks 7 and 8. The mathematical side is in a separate video that will be available in the Brightspace environment. For all updates, keep an eye on the announcements, and all the materials will be under content. The workshops can be found under virtual classrooms, and I will see you next time.